Hello, hello, hello. In this episode of What's the Big Idea, we're going to talk about problems in which the acceleration of an object is constant. And I'll start off by saying, this is an unusual episode of What's the Big Idea because, in some sense, I want to convince you that problems with constant acceleration are really not all that important. It's a rather special case, but it's one that it lends itself to writing textbook problems that are solvable. And so it often, in my view, gets overemphasized in an introductory mechanics course. So we'll try to avoid the pitfall of overemphasizing these kinds of problems, but they are worth talking about a little bit. So let's dig in. So we'll start off by considering the case in which the motion occurs in just one dimension. So objects are moving back and forth in a straight line, and we'll assume that the object is accelerating, but the value of the constant of the acceleration remains constant, and it'll have a constant value which we'll call a. So if an object is undergoing a constant acceleration a, let's make a plot of what its velocity is going to be as a function of time. So let's assume that at time 0, uh, the object has some initial velocity v naught. So constant acceleration means that as time progresses, the value of the velocity will change linearly. It'll be a straight line plot. And if the acceleration a is a positive number, then that line will have a positive slope the way I've drawn here. Or algebraically, we can write that the velocity as a function of time is equal to v naught plus a times t. And then suppose we want to make a plot of the displacement of this object as a function of time. Well, we know from our previous discussion that the displacement at any particular time t is given by the area under the velocity versus time curve. And it's easy to write down a algebraic expression for what the area under this curve is. At some particular time t, we can divide, this is sort of a trapezoid here, we can divide the trapezoid into a rectangle and a right triangle. And the area under the curve then, the displacement as a function of time, is equal to the area of the rectangle, which you can just see is v naught times t. And the area of the right triangle is 1/2 at squared. So if we make a plot of this, it's going to be some sort of part of a parabola here, parabolic shape, if we plot the displacement as a function of time. And so we were able to write down these nice, what we call analytic solutions, where you just plug in the time. If you want to know, what the velocity is at some given time, you just plug into this formula. And if you want to know how much the object has been displaced at a certain time, you just plug in the time into this formula and you get the answer. And then if you're reading the Wolfson text, you can combine these equations and you can get a set of equations that let you solve for different quantities in terms of different other quantities. So the whole thing is very convenient. And as I mentioned at the outset, it's easy to write textbook problems that are basically, they're rather robotic. You sort of, plug into these equations and you can get the answer. So for example, here's a sort of typical problem. I actually got this out of the Wolfson textbook. A rocket rises with a constant acceleration. We're not told what it is. We're given the final altitude that it achieves, at which point it is going at some speed, and we're asked two questions. What is the rocket's acceleration, and how long does the ascent take? Well, it's easy to solve this sort of thing. We just need that table. Well, so to solve part A, we're being asked for the acceleration, and we're given information about the final velocity. I'm sorry, the final value of x and the final velocity. So basically, you need to figure out which of these equations has the right variables in it. We need something that has the acceleration in it, a final velocity and a final position. So we're looking for something that has an x, a v, and an a in it. We don't care about time. We're not being asked about that in part A. So this is the equation we want. So we're going to use v squared is equal to v initial squared plus 2a times, I'm going to write uh, x minus x naught as just delta x, the change. That's the displacement. And in this problem, we're given the final velocity of 2.8, and I'm going to write everything in SI units. So I'm going to write this as 2,800 meters per second quantity squared is equal to the initial velocity squared. Well, we assume that the rocket started off at rest on the launch pad, so we can ignore this term. And then it's just 2 times a, and then the change in position is 85 kilometers, which is 85,000 meters. And then this is just a simple equation in which there's just one unknown, the quantity A, which is the quantity of interest. And then you just solve algebraically for that. I won't take the time to do that. I'm sure you know how to do that. And then in part B, I'll let you think about it for a minute before I give you the answer. How long does the ascent take? So the question is, which of these equations do you want to use? Let you think about it for a minute. Okay, have you thought about it? Good. So we're looking for an equation that does involve time. And now we know the acceleration of the rocket. So since we know the acceleration, the simplest equation to use is this one. We know the final velocity, the initial velocity was 0. We know from part A have figured out the acceleration, so you can just solve for the amount of time that the trip takes. So as I said, these problems are, at the end of the day, pretty straightforward. They're rather robotic, and I don't find them all that interesting, really, to be honest with you. And not only that, but they're not that realistic often. You know, in the real world, it's not so often that you deal with constant acceleration. But sometimes you do, so it is worth talking about. Now, an important example where you do have constant acceleration is projectile motion. So if we consider the case of an object thrown into the air near the Earth's surface, and let's suppose it's a situation where it's a good approximation to neglect drag. So maybe this is a shot put event, so the drag forces are going to be negligible compared to the force of gravity. And in that case, the constant acceleration, it's a vector quantity, but it is just equal to this vector g, which is a vector pointing straight down and of magnitude 9.8 meters per second squared. And so in that case, you really have really it's constant acceleration in both in the x and the y direction. In the horizontal direction, the acceleration is constant; it's just equal to 0. And then in the vertical direction, there's a constant acceleration downward of minus 9.8 meters per second squared. So projectile motion problems are a case where often to a good approximation, the acceleration is constant, and you can use the approach that we just outlined to answer lots of questions. Uh, so you'll have some opportunity to work on problems like this, but as I said, I don't want to overemphasize it because the problem is, since this is something people learn early in the course, they tend to memorize these equations, and then it's human nature to want to apply them to all sorts of situations, including many of which where the acceleration is not constant. So we'll spend a lot of time in this course talking about things like masses connected to springs or orbiting satellites in which the acceleration is certainly not constant, and and in that case, it's really not at all okay to use the formulas that were in that table. So that's an important caveat. That's really the big idea is in this episode is to not over apply these problems involving constant acceleration. So that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.